Alright, so this is an introduction to buffers. We're going to talk about their purpose and what criteria are necessary to have a buffer, how they work, and exactly how they respond to the addition of the strong acid or strong base. And then we're going to do quite a bit of calculation practice of determining the pH of the buffer system itself, and then also seeing how that pH changes with the addition of a strong acid or strong base. So, first of all, the purpose of the buffer solution or the buffer system, is to basically maintain a fairly narrow pH range. This is especially important in biological systems, in other chemical reactions that we'll study, but in particular in biology. And I use the example of the human blood pH needs to stay in a range of about 7.35 to 7.45 in order for you to maintain health. And if it varies much out of that range, then it can cause serious health risks and or death. And so they play a very important role in many biological systems. And so what does it take to have a buffered system? Well, first we need a weak acid. You can also do it with a base, but every example we're going to work this year is going to be a weak acid. And it can't be a strong acid, but which weak acid you choose depends on the pKa of that acid, because you want the pKa of the weak acid to be within plus or minus 1 of the desired pH that you want to stabilize the system at. And of course, pKa simply means the negative log of the Ka. Ka we saw in our introduction to acids. It's the acid dissociation constant, which is equal to the concentration of the H plus ions times the concentration of the anion divided by the concentration of the acid itself. And so a very strong acid will have a high Ka because there will be a lot of H plus ions in solution, and a weak acid will have a very low Ka. As a result, the pKa will be, for a very weak acid, very low Ka will have a relatively high pKa. And that doesn't surprise us because it'll be less acidic. The third criteria is that you have to have a common ion salt. And we've seen already what common ions do in solubility and in other applications, but this is what really makes the buffer work. It has to be the anion, right, that corresponds to the weak acid. So, for example, if your weak acid is hydrofluoric acid, then you want something that has a fluoride ion. So sodium fluoride or potassium fluoride. Similarly, in your blood system, we have carbonic acid, and so the common ion is going to be a carbonate ion, usually in the form of sodium bicarbonate or sodium hydrogen carbonate. But any salt that provides the common anion will work. But the final criteria is that they have to be relatively close concentrations, and I'm talking about the salt concentration and the weak acid concentration. And you'll see mathematically in a little while why that matters. But when those two start to vary from each other, that's when we get a wide range of pHs within the system. And then we need a large volume of the weak acid and the common ion, because I say relatively large volume because it has to be large compared to the amount of strong acid or strong base that's being added to the system. And we refer to that as the buffering capacity, because once you exceed that, then those ratios get off, and you'll see again mathematically why that becomes an issue. All right, so how do buffers actually work? Well, let's just take an example, hydrofluoric acid. If I have a solution of hydrofluoric acid, it's going to break down into H plus ions and fluoride ions, but not very much, right, because it's a relatively weak acid. And so I've underlined the weak acid in blue and its corresponding conjugate base in green. So, so long as, so first of all, let's think of when we don't have a buffered system. If we don't have a buffered system and you added a strong acid like hydrochloric acid to this solution, you'd basically just be pouring in H plus ions, right? Because the definition of the strong acid is that it completely dissociates into H plus and Cl minus. Well, if there's just the HF solution, there's very small concentrations of H plus and F minus, and so you're just going to be dumping a whole bunch of H plus ions into the solution, and we'd expect the pH to drop dramatically, right? Because the H plus concentration is going to increase so dramatically. But here's the beauty of having the common ion. If you have sodium fluoride, for example, another source of fluoride ions, then when you dump in these extra H plus ions, that concentration goes up, but then the fluoride ions combine with them to reform the weak acid. And so we do have a drop in pH, but it's much, much smaller than it would be had the common ion not been present. And so this is the functionality of the buffers. So I'm just going to rewrite it again so that we can see what's going on here. And we're going to contrast what happens with the addition of a strong acid versus the addition of a strong base, because these two first steps here are the hardest to get used to, but once you get them, it'll make buffer calculations much easier. So for example, again, if we have our hydrofluoric acid and some source of fluoride ions, the conjugate base, again, it can be sodium fluoride, potassium fluoride, doesn't matter. Then if we add a large amount of H plus, actually, let's say a large amount. I don't mean a large quantity because the volume has to be fairly small, but if we add a source of a lot of H plus, in other words, strong acid, then we would expect the pH to drop dramatically. However, if there is sufficient fluoride ion present, that conjugate base will then react with, combine with the H plus ions from the strong acid and reform the weak acid. And of course that then doesn't drop the pH as dramatically. Similarly, if we add a base, then what's going to happen? Well, when you add the acid, who can help you? The conjugate base, right? Because the conjugate base can help neutralize the strong acid. Well, if you add a strong base, then what's going to help to neutralize the strong base? Well, that is the weak acid. And so we're going to write that first. The weak acid then will combine with the hydroxide ions to produce what? Water and the conjugate base. So again, note the roles of acid and conjugate base. When we add a strong acid, the conjugate base forms the weak acid. And when we add a strong base, the acid forms the conjugate base. And so in both of these cases, again, we will see a change in pH, but it will be very, very small compared to the change that we would see without the buffering system. And so this is how buffers keep pHs within fairly small ranges. All right, so another thing we're going to need to know how to do mathematically is determining the pH of the buffered solution, or if we know what the desired pH is, then we need to know what ratio to use of what particular weak acid between the weak acid and the conjugate base. And to do that, we're going to use an equation called Henderson Hasselbach equation. And I mentioned in class that this is not something you're going to have to derive. It's actually given on the equation sheet. But just to show that this isn't just smoke and mirrors, I did the derivation for you. Basically, we start off with the the acid dissociation expression. Ka is the concentration of H plus times the anion concentrations over the concentration of the acid. And then just with some math, I rearrange by multiplying both sides by the concentration of the acid dividing both sides by the concentration of the anion, and then I just reverse them just because it's easier to see what I do from here. And then if I take the negative log of both sides, that's P, then I get pH equals pKa minus log of the HA over the A minus. Well, you may have to trust me on this if mathematically you don't see it, but I can switch the I can change the sign of the in front of the log to positive if I reverse the roles of the HA and the A minus. And so rewriting those makes that a positive expression, and I get this thing again, which is called the Henderson Hasselbalch equation, and it says that the pH is equal to the pKa plus the log of the ratio of the conjugate base over the weak acid. Now let's again think about what that means. If I add a strong acid, then we said that the conjugate base is going to react with the strong acid and produce the weak acid. And so what's going to happen is the concentration of the conjugate base is going to go down. The concentration of the conjugate acid is going to go up. And this term is going to end up being less than 1 if they started off equal. And a log of less than 1 is going to mean a negative number, and the pH is going to drop. But again, it's going to drop slightly compared to what it would have done had we added just the strong acid to a non-buffered solution. Similarly, if we add the strong base, then the acid concentration goes up, the conjugate base concentration, the acid concentration goes down, the conjugate base concentration goes up. That log becomes log of a number greater than 1, and that makes it positive, and so the pH goes up. But again, not nearly as dramatically had we not had the buffered solution. And so that's Henderson Hasselbach. I do want to point out a couple of things before we move on, and that is we see a couple of the criteria that we talked about earlier. One, that second criteria that says that the pKa should be within about plus or minus 1 of the desired pH. And you can see that here because we want, when they're equal concentrations, log of 1 is 0, and that's when the pH does equal the pKa. But then, again, there's that ratio. So long as we have large volumes of the common ion in the acid, then that ratio doesn't deviate much from 1. And so the raise and drop in the pH is fairly small compared to the original value. And that was, again, about the buffer capacity. All right, so this is Henderson Hasselbach equation. We're going to see it used quite a bit later. All right, so let's now take a look at the buffers practice that I gave you. And first of all, notice that the question 1 starts off with 0.45 moles of hypoiodous acid. They give you the Ka there, 2.3 times 10 to the negative 11. So it's a very, very weak acid. And I'm adding it to 1 liter of solution at standard temperature. So what I want to note about all of these problems is we're going to start you off easy. We're just going to give it to you in terms of moles, and we're going to say we have a liter of solution, and we're going to assume that that liter volume doesn't change. As we get more advanced later, then we'll have to be careful. When we start mixing stuff, we're going to change total volumes. We're going to have to be careful how that affects the concentrations. But for now, we're going to kind of enter the shallow end and just kind of ignore any volume changes. All right, so we have this initial pH is the first question. So what is the pH of a 0.45 molar hypoiodous solution if that is its Ka? Well, that's not a buffer, right? That's just what we learned when we did Introduction to Acids. And so we're going to write the equation of what happens. We have this HIO that's going to break down into H plus and IO negative, but not very much because of this very, very tiny Ka. And so I can write the Ka expression. It's going to be the concentration of H plus times the concentration of the hypoiodide ion over the concentration of the acid. and it might behoove us to write an ice chart. The initial concentration of the acid is 0.45. The initial concentrations of the two ions is 0, and it's going to change by a value that I'm just going to call x, so that the equilibrium concentrations will be 0.45 minus x and x respectively. And so just continuing my Ka expression now with these values, I can write it as 2.3 times 10 to the negative 11 equals x times x, or x squared, over 0.45 minus x. And of course, that 2.3 times 10 to the negative 11 means it's a very weak acid, and so that change of x is going to be completely negligible compared to the 0.45, and so I can cross that out and ignore it. And then just as a matter of multiplying by 0.45 and taking the square root to get x, which is 3.2 times 10 to the negative 6. And that, as you can see from my ice chart, is the final concentration of H+, and so I can use that to calculate the pH. Just take negative log of 3.2 times 10 to the negative 6, and I get the pH of 5.49. And so that is the pH of this weak acid when it's just a 0.45 molar solution and no buffer. Now again, what did it form when it dissociated? It formed a conjugate base, which is the hypoiodite ion. And so when I take sodium hypoiodite, and in question B, and I can say that that will break down into sodium ions and hypoiodite ions. And those hypoiodite ions are going to act as bases, right? They can accept a proton in solution and form the acid. And so if it is a base, then it has a base dissociation constant, or a Kb, and therefore it has a pKb. I can take the negative log of that Kb value. And so that's what we want to do in part B, and that is to figure out what that Kb is. Well, there's two approaches I can use. One is I can know that the K of water, Kw, equals Ka times Kb for acid and conjugate base pairs. And then what follows mathematically from that is that pKa plus pKb for acid conjugate base pairs is going to add up to 14. And so I'm going to show you how to use both of those approaches. It turns out that the first approach is actually the better one because we're going to use the Kb later, but either one of these would work. And so at 25 degrees Celsius, Kw is 1 times 10 to the negative 14. And so that equals the Ka, 2.3 times 10 to the negative 11 times Kv. So just divide both sides by that Ka, and that gives me a Kb of 4.3 times 10 to the negative 4. And negative log of that number gives me the pKb of 3.36. Alternatively, I could have jumped straight to taking the Ka and finding the pKa, which is negative log of 2.3 times 10 to the negative 11, which is 10.64, which we're going to use that again in a second as well. Subtract that from 14, and I get 3.36. So again, both approaches give me the same number, which I'd expect them to, and they both have advantages in different contexts. So it's good to know how to use both. Again, it's not really two different approaches, it's just the same math done in different orders. All right, so then question C says, find the pH of a 0.45 molar solution of sodium hypoiodite. Well, we just said sodium hypoiodite is a base, or at least the hypoiodite ion in that solution will act as a base. And it will react with the water to accept a proton and form the weak acid, and therefore raise the OH concentration. And so again, I can go to an ice chart. I know that I can write a Kb expression and then form an ice chart. I know I'm starting off with 0.45 molar hypoiodite ion. It's going to go down by some value, call it x, which is going to be the amount that the acid concentration goes up and the OH minus concentration goes up as well. I just found the Kb when I was trying to find pKb, And so I can plug that into my KB expression. 4.3 times 10 to the negative 4 equals x times x over 0.45 minus x. But here I've got to be careful. 10 to the negative 4 is not small enough. This is a relatively weak base, but it's not weak enough to just ignore that minus x. And so I am going to have to do a quadratic. But algebra tells me that that's the quadratic. Plug it into my calculator and solve for the roots. And I get a value for x, which is the concentration of OH minus of 0.014. Negative log of that tells me that the POH is 1.85, and then the pH, which is 14 minus that, is 12.15. And so again, that doesn't surprise me a lot, right? That it is pretty basic because being a very, very weak acid, the conjugate base is going to be relatively stronger, and that ends up giving me a pH of 12.15. Now we get to our first actual buffer. Part D says, hey, let's take a solution that has 0.45 molar sodium hypoiodite and 0.45 molar hypoiodous acid and put them together in a buffered solution. So what is the pH of that? Well, again, I can use two different approaches to solve this. The first is not using the Henderson Hasselbach equation. And I'm going to show you that sometimes that's a good approach. Usually, when we're determining the pH, we're going to go Henderson Hasselbach, but it's good to work it with both, with and without. And then again, as we work problems, you'll see when it's appropriate to use and when it's not. But I'm going to write my expression. I have the weak acid breaking down into H plus and IO minus. And I can then say that the acid concentration starts at 0.45, but the common ion, the conjugate base concentration, also starts at 0.45. So that's different than what we had before, right? There is quite a bit of the common ion already in solution. And so as a result, that's going to change my final concentrations. When I take the Ka expression and plug in these values, I get 2.3 times 10 to the negative 11 equals x times 0.45 plus x over 0.45 minus x. Again, that 2.3 times 10 to the negative 11 says that change x is tiny. It's completely insignificant compared to both 0.45s, whether I add it or subtract it. And so those two go away. And the 0.45s, 0.45 divided by 0.45 is just 1. And so the x ends up being 2.3 times 10 to the negative 11. Well, if x is 2.3 times 10 to the negative 11, then pH is just the the pKa that we found earlier. It's 10.64. And so the pH, when we have equal amounts of or equal concentrations of the weak acid and the conjugate base, ends up being the pKa of the weak acid that the buffer is built on. Now let's do the same thing using the Henderson Hasselbach equation. Henderson Hasselbach says that pH equals pKa plus log of the ratio of the weak acid, the conjugate base to the weak acid. Well, what is that? That is a negative log of the Ka plus the log of 0.45 over 0.45. Well, 0.45 over 0.45 is 1. What is the log of 1? Well, 0. So it ends up being the negative log of the Ka, which is 10.64, plus 0. And so what is the pH? It's 10.64, which is exactly what we got when we didn't use the Henderson Hasselbach. So it doesn't surprise us, but it just shows two different approaches to solving the same problem. All right, so now we're going to do what buffers are made for. We're going to add a strong acid to the buffered system and see what happens. In this case, we're going to add 0.2 moles of HCl. Well, we already mentioned HCl is a strong acid, and so adding 0.2 moles of HCl is adding 0.2 moles of H+. And again, what I always want you to ask yourself is, how's the buffered system going to respond to this change? And if I'm going to add a bunch of H+, who can help me? Well, the conjugate base can help me. And so what's going to happen, and when I add the H plus, is the H plus is going to combine with the conjugate base, which is IO minus, and reform the weak acid. I'm going to draw an ice chart. Starting concentration is 0.20 of the H plus and 0.45 of the 0.45 of the conjugate base, and the starting weak acid concentration is 0.45 as well. And so I've got everybody present. And notice again that 0.2 is not from the weak acid, right? This is straight from the HCl. So then I've got kind of a limiting reactant type question. When the H plus starts being neutralized by the conjugate base, what do I run out of first? Well, in this case, I'm going to run out of the H plus. And so the change is going to be minus 0.20. Well, finishing out the ice chart, I end up with a 0 of the H plus that I added, 0.25 of the conjugate base, and 0.65 of the weak acid. Now, neither of those values is 0, and so I can use Henderson Hasselbach. So let's do that. So pH equals the pK plus plus the log of the conjugate base concentration over the acid concentration. The pKa I've already done several times, but I'll show that in a second. And then log of what's the concentration of the conjugate base now? It's down to 0.25. What's the concentration of the weak acid? It went up to 0.65. Again, that number is less than 1, and so I expect log of that number to be a negative number, causing the pH to drop. And it does drop, but only drops by 0.41. And so the pH drops from 10.64 to down 0.41 to 10.23. Now, that's what I expected. I expected the H plus to lower the base concentration and raise the weak acid concentration, which caused the pH to drop. But because of the presence of the buffer, it's not a very big change. That number is negative, but it's a small change in the pH versus if I had just added the H plus to a non-buffered solution. And so again, that's the buffer at work. That's the whole purpose of the system. All right, so then in question F, we're going to do the same thing, only this time we're going to add a base. And so the question you have to ask yourself is, well, what's going to help you when you add a base? If I add a bunch of OH minus, what's going to start to neutralize it? And that is, of course, the weak acid. So I'm going to write the equation of what's going on. We're going to take OH, and it's going to react with a weak acid, causing a drop in the concentration of the weak acid, but an increase in the concentration of the conjugate base. And draw an ice chart. Here's your starting values. And then ask yourself, okay, which one of those is going to run out first in the neutralization? And of course, it's going to be the OH minus this time. So the change is going to be minus 0.35. And then it's going to cause the concentration of the conjugate base to go up 0.35. Are either of those two numbers 0? Nope. And so I can use Henderson Hasselbach. Plugging in and solving tells me that the concentration of the conjugate base went up to 0.80. The concentration of the weak acid went down to 0.1. So that term ends up being log of 8. I add that to the 10.64 and I get 11.54. Now again, that doesn't surprise me. The concentration goes up, the pH goes up because I added a strong base, making this term more than 1 and making log of that term positive. But it's a very small change in the pH versus adding 0.35 moles of hydroxide ion to a non-buffered solution. All right, the next one, we're going to add 0.45 moles of the hydroxide to our buffered solution. Now, right away, you can see that something weird is going to happen here. we've got equal concentrations of the hydroxide and the weak acid. And so we're going to run out of both, right? Both of those are going to go to 0, and the concentration of the conjugate base is going to go up to 0.9. So because of that 0 there, I'm not going to be able to use Henderson Hasselbach. So what do? Well, the neutralization has taken place. We've kind of reset the clock, and now we just look at that last term. We now have 0.90 molar hypoiodite ion. In other words, the conjugate base. Well, what's that going to do? It's got water, and so it's going to reverse what we had before. It's going to react with the water to reform the weak acid and raise the hydroxide ion concentration. After all, it is a base, right? It's a conjugate base, and so it's going to raise the OH concentration itself. And so I'm going to use that and my KB that I found earlier. Do my ice chart here, right? It's going to change how much. Call it a little change X. Take your KB expression. And now it's back to what we've been doing for weeks, right? Just X times X over 0.9 minus X. Careful though, can I just knock out that minus X? No, because 10 to the negative 4 is not small enough. So I do have to do quadratic. But thanks to my calculator, it's an easy process. And I can find that the hydroxide ion concentration is 0.020, giving me a POH of 1.7 and therefore a pH of 12.30. So now it jumped up quite a bit that time, right? I mean, we've now gone over 1.5 on our pH scale from the starting pH. That means that we're pretty much exceeding our buffering capacity, which doesn't surprise me because we added just as much OH minus as we had the weak acid in the starting buffered system. And so we're exceeding the capacity, and so we're going to see pretty dramatic changes in the pH now. All right, so now looking at the next question, you can anticipate that we're going to see a similar situation. We're adding 0.45 moles of HCl, and so this time, who's going to help you get rid of H+? Well, the conjugate base is, but because we have equal concentrations, we're going to run out of both of them. We're going to end up with 0.90 molar weak acid. Can't use Henderson Hasselbach, but we can do what we've done for weeks. We can say, hey, if you start off with 0.90 molar HIO, it's going to break down into H plus and IO according to its Ka, which is that 2.3 times 10 to the negative 11. Now, though, that small Ka says I can ignore the minus X term and makes my math a little easier, avoids the quadratic. H plus concentration is 4.5 times e to the negative 6, making pH 5.34. And again, that's a dramatic change. But that's what I expected because I've exceeded the buffering capacity. All right, so then the next two problems, we're actually going to just blow right through the buffering capacity. We're going to add way too much of the strong acid or strong base and blow the buffer wide open. And so I'm just going to work one of them to show you the example, and you can figure out the hydroxide concentration, or excuse me, the hydroxide example yourself. But here it is, right? It's going to start off the exact same way. I'm adding H+, who can help me? The conjugate base. So the H+ is going to combine with the IO- to reform the weak acid. Again, who's smaller? What I'm going to run out of? I'm going to run out of the hypoiodite ion in this case. And so the change is going to be the minus 0.45. That's going to cause the weak acid concentration to go up to 0.9, but guess what? I don't care. And the reason I don't care is because after neutralizing all the common ion in the IO-, I've still got 0.20 concentration of H+ ions from the strong acid. And so think about it. If the Ka of the weak acid is only 2.3 times 10 to the negative 11, does it matter how much of that 0.90 breaks down into H+ concentration compared to the H+ that I already have from the HCl which is a strong acid, of the 0.20? And the answer is no, it's not. So I can completely ignore that and just take the pH from the H plus concentration of the 0.20 molar. And so you just do negative log of the 0.20, and that gives me the pH of 0.70. And so that is a ridiculously low pH, right? And it doesn't surprise me, though, because I blew right through the capacity of my buffer. And again, you can anticipate that in J, we're going to do the exact same thing, only the leftover hydroxide ion is what's going to drive the pH of that final solution.